Welcome to our quantum deep dive.
Today we're going to split the atom. Well, in theory anyway. We're diving deep into the profound, world-changing physics of nuclear fission. Our guide for this explainer is a really incredible essay by Georg O. Schneppot, which gives us a map to this amazing source of power.
So here's our plan. We're going to start with what was basically a complete accident in a Berlin lab. Then we'll get right to the heart of it, this invisible wall they call the fission barrier. From there, we'll check out the brilliant competing ideas scientists came up with to explain the split, see how modern computers can now simulate the whole event, and finally, we'll look ahead to a truly mind-bending quantum future. You know, our story doesn't begin with some colossal bang, but with quiet, deep confusion in a lab in Berlin. It's 1938, and a team of scientists were just methodically trying to create heavier elements. Instead, they found something that wouldn't just redefine physics, but in a few short years would redefine the entire world. Otto Hahn and Fritz Strassmann were firing neutrons at uranium, hoping to make something new, something heavier. But the results they got were just plain weird. Instead of a heavier element, they found barium, which is about half the size of uranium. At the time, it made zero sense. But the key, the real aha moment, came from Lise Meitner, their brilliant former colleague who'd been forced to flee Germany. Working with her nephew Otto Frisch, she realized the uranium nucleus wasn't just chipping off a piece, it was violently splitting in two. They borrowed a term from biology and called it nuclear fission. And with World War II right on the horizon, the race to understand this terrifying new power started, well, pretty much overnight. Yeah, and this quote just perfectly captures the shockwave that followed. The news electrified the scientific community. On the one hand, you've got this promise of nearly limitless energy, a stunning confirmation of Einstein's E=mc², where a tiny bit of mass becomes a staggering amount of energy. But on the other hand, you have the chilling, frankly terrifying potential for a weapon of truly unimaginable power. The atomic age had officially and irrevocably begun. So if splitting the atom unleashes all this incredible energy, you kind of have to wonder, why don't heavy elements just fall apart all the time? Well, the answer is this idea that's honestly at the very core of this whole story, the fission barrier. The best way to think of it is as an invisible wall the nucleus has to break through before it can even hope to split. Exactly. Think of the nucleus as this tiny little battlefield for two of the universe's most fundamental forces. On one side, you've got the strong nuclear force. It's this incredibly powerful but really short-range glue that holds all the protons and neutrons together. On the other side is the Coulomb force. That's just the natural repulsion between all those positive protons, and they are pushing hard to fly apart. The fission barrier is just the amount of energy you need to put in to stretch that nucleus just enough for that repulsion to finally win the tug of war and tear the whole thing in two. Okay, but this is where it gets really weird. This barrier is usually several mega electron volts high, and on an atomic scale, that's a huge amount of energy. So that leaves us with this huge kind of paradoxical question. We know for a fact that some nuclei split all by themselves in what we call spontaneous fission. But how on earth is that possible if they don't have anywhere near the energy to get over that massive barrier? The answer is pure quantum weirdness. It's called tunneling. See, in the wacky world of quantum mechanics, a nucleus isn't just a tiny solid ball. It's also a wave of probability. And that means it has a small but critically non-zero chance of just appearing on the other side of that energy barrier without ever having the energy to actually climb it. It's like a ghost walking straight through a solid wall. For spontaneous fission, this is the only way it can happen. The nucleus literally tunnels through a barrier that in our world should be totally, absolutely impossible to get through. Right, so at this point, scientists knew it was happening, and they had a basic idea of this energy barrier it had to overcome. But to really get it, to predict it, they needed a model, a theory for what the nucleus actually looks like on the inside. And the first two big ideas came from completely different, competing points of view. So first up, you have the liquid drop model. And it's a really simple, kind of beautiful idea. Just imagine the nucleus is a tiny drop of charged liquid. The strong force acts like surface tension, holding it all together. You add some energy, maybe you hit it with a neutron, and the drop starts to wobble and stretch. And if you push it far enough, it splits. It was a great classical analogy, but there were these weird little details it just couldn't explain. And for that, you needed a completely different way of thinking, the shell model. This model goes full quantum, seeing the nucleus not as a blob of liquid, but as this highly structured system where protons and neutrons fill up distinct energy shells, almost exactly like electrons do in an atom. And this is where the shell model just blew everyone away, because it had incredible predictive power. Its greatest moment was explaining the magic numbers. For years, physicists had seen that nuclei with certain numbers of protons or neutrons, like 8 or 20 or 50, were way more stable than their neighbors. Why? Well, the shell model showed these numbers weren't random at all. They were the points where the nuclear shells were perfectly full and stable, kind of like noble gases in chemistry. And that was the whole point. The fission barrier wasn't just some generic wall. Its height, its shape, everything about it depends on the nitty-gritty quantum details of that one specific nucleus. So, what's the reward for getting past that barrier? Well, it is enormous. A single uranium fission event lets loose about 200 mega-electron volts of energy. And to put that in perspective, that's literally millions of times more energy than you get from a chemical reaction, like burning fuel. As you can see, the vast majority of it, about 85%, is instantly turned into pure kinetic energy, the two new fragments just flying apart from each other at insane speeds. The rest is carried off by stray neutrons, gamma rays, and the decay of those fragments later on. So for decades, you had these two competing ideas: the simple, intuitive liquid drop and the complex but more accurate shell model. For a long time, they were treated as totally separate. But, modern physics, it's all about bringing ideas together. The real breakthrough came when somebody figured out a clever way to combine the best of both. And this hybrid is called the microscopic-macroscopic model, and honestly, it's just a brilliant idea. You start with the big picture, the broad strokes, from the liquid drop model to get the general shape of the energy landscape. Then you start layering on top all the fine-grained details from the shell model, all those quantum effects, the magic numbers, the structural quirks, even how protons and neutrons like to form pairs. The final result is this incredibly detailed, multidimensional energy map that can predict, with amazing accuracy, the most likely path a nucleus will take as it splits. And today, with the kind of power we have in supercomputers, we can take it to a whole new level. We've got these advanced simulation methods that let us model the entire fission process in real time, from that first jolt of energy all the way to the fragments separating. We can literally watch the quantum wave functions of every single proton and neutron evolve as the nucleus rips itself apart. We've gone from simple analogies to full-blown dynamic quantum simulations of the atom's core. It's incredible. All right, so this brings us right up to the cutting edge, and maybe a whole new chapter in the story. For over 80 years, we've basically seen fission as a source of raw, immense power, for good or for bad. But what if the complex quantum dance inside the nucleus could be a resource itself? What if this 20th century discovery could actually fuel a 21st century technology? And this is the huge, kind of mind-bending question that's driving a whole new field of research. We already use the delicate quantum states of atoms and electrons to build the first quantum computers. So the question is, could we do the same thing with the much more complex, much more stable states inside the nucleus itself? Okay, so the key here is this thing called a nuclear isomer. Basically, it's a nucleus that's been kicked up into a higher energy state where it can stay stable for seconds, hours, even years. In theory, that amazing stability could make them perfect quantum bits, or qubits, because they'd be naturally shielded from all the noise that messes with current quantum computers. Now, the challenge is immense. Controlling these states is incredibly hard. But there are some tantalizing possibilities. An isomer of thorium-229, for instance, has an excited state that's at such a low energy, we might actually be able to control it with lasers we have today. That could open the door to amazing new tech, like a nuclear clock that's unbelievably accurate, or maybe, just maybe, a true nuclear qubit. And all of this is building toward an even bigger, even crazier idea: quantum control. Right now, we trigger fission by basically hitting a nucleus with a hammer and just seeing what happens. Quantum control asks, what if we could use finely tuned lasers or quantum fields to guide a nuclear reaction down a very specific path? Could we choose which fragments get made? Could we figure out a way to turn long-lived nuclear waste into something harmless? It's a massive scientific challenge, but it's a total shift in thinking, from brute force to precise quantum control. And that really brings us to this powerful final thought from the essay by Jörg Owe Schneepatt. This idea just completely reframes the entire legacy of nuclear fission. The very process that defined the raw, brute force power of the 20th century could become a tool of subtle, precise quantum control in the 21st. It's a truly fascinating pivot from brute force to quantum finesse. So, we want to leave you with this one question to think about. We've gone from a baffling lab result in 1938 to the quantum heart of the atom, all the way to a future where that nucleus itself might power a quantum computer. It's an absolutely stunning journey for one physical process. Could the discovery that defined the atomic age really end up powering the quantum future? It just goes to show you our understanding of fission is still changing, still evolving, and it's constantly pushing the boundaries of what we thought was possible. Exactly. It's just the perfect example of how one single fundamental discovery can keep opening doors to technologies we are only just now beginning to imagine. The journey from that lab in Berlin to the theory of nuclear qubits, it's just a powerful testament to where curiosity can take us. Thank you so much for joining us for this deep dive. To read the original essay by Jorgo E. Schneppe that inspired it all, please visit schneppet.de. Goodbye. Goodbye.
Schneppet.de is a private project by Jorgo Schneppet dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.